Where is it? Okay. Check. Okay. Okay, so can you guys see the slides now?
No, Doktor.
Yep. Boleh nampak?
Okay, nampak dah.
Ya, kan.
Okay. Right. I think yesterday we have been introduced with the first part of this chapter 2, thermodynamics and potential. So basically, as what I've told you, thermodynamics consideration is sometimes important in any electrochemical reaction, because in order to understand what will be the behavior or what will be the rate of reaction, so of course we need to study at different temperature, because different temperature will give different profile or different performance, right? And I have believed that we have seen a few equation related on thermodynamics. Okay, as what I have mentioned, this one is the free energy. Okay, Faraday's equation. Okay, delta G is equal to minus NFE, and then you also have another equation that is related with entropy. Okay, and you can also calculate delta H, which is enthalpy, using a Barnhoff equation. Delta G plus with temperature multiplied with delta S. Okay. So we are going to look on examples. Yes, Mahdi, anything?
What's the difference between delta G and delta G naught?
Delta G and delta G naught, the same thing. I think delta G, it means that the experiment is undergone not in the delta G naught undergone in the standard condition, 1 atm pressure, temperature 25 degrees Celsius, concentration equals to 1 molar, but without, I mean, delta G, I mean, just a normal delta G without delta G naught, it is not in the standard condition, which means the pressure is not 1 atm, temperature is not 25 degree, and concentration is not 1 molar.
So okay, that means the difference only delta G naught use E naught.
Sorry again?
That means that the difference between delta G and delta G naught use only E naught.
If you notice, for delta G naught and E naught, it means that the experiment is basically undergone at the standard condition. So as I mentioned, you will get delta G naught when the experiment is undergone in standard condition. You will get delta G only if the experiment is undergone not in the standard condition. Okay?
Okay, doctor.
All right, so we are going to look on example 1. The EMF for the cell silver bromide, metal bromide, okay, connected with mercury bromide, Okay, and the value of potential, the half of the cell potential, okay, for this one is basically the reduction, the oxidation reaction will be as follows. So over here, you will see that the value of E cell, which is the standard potential, okay, it's equal to the E naught over bromide, silver bromide potential. So I think allow me if I can draw over here. Let me just, okay. So for this experiment, you have, okay, you have a silver, Ag, and then another one, which is basically mercury, okay, so connected together in a solution. So the solution is basically metal bromide, any types of metals, MBr. So the common ions over here, if you see, is bromide. It is a common ion for the anodic side and also the cathodic side. Okay. So what happened over here is that there's heat applied. It is being heated, okay, and at a different temperature, 15, 25, and 35, it will give different E cell. This is actually overall cell because we know that E cell, okay, in standard condition, is equals to E naught cathode minus E naught anode. Okay, so this one I think I forgot to put naught. Okay. As you can see over here, okay, for this kind of a reaction, okay, these two, okay, will experience oxidation, and this, okay, two will form reduction. So basically, each and every electrode have its own potential value. For example, for silver bromide, okay, so this actually have its own standard potential value, which we noted it as, okay, Br minus AgBr. Meanwhile, for this one, E naught equals to Br Hg2 Br2. Okay, all right. So the overall cell potential is over here, E cell, E naught cell. Okay, and you will get E naught cell by basically subtracting the cathode versus the anode. Okay, so meaning that over here, you will get E naught cell by basically considering E naught of cathode, which in this case Br minus Hg2 Br2 minus E naught Br AgBr. Is it okay? You guys can follow?
Yes, Doctor.
Yes, Doctor.
Okay. So the value of the anodic potential, this one is given at a different temperature. The value of E cell at different temperature is also given. So question A, calculate the potential, the standard potential of cathode. Okay, this one we want to find E cathode. Okay, at each temperature and find the equation that relates, okay, cell potential and the potential for cathodic as a function of temperature. Okay, so to answer question number A is basically very simple. Okay, you can calculate the cathodic potential, because for example at 15 degrees C, okay, substituting this one, so you know that you will get E naught is equals to E cell, E naught cell, okay. This one you just carry it forward, then you will get plus E naught BR AGBR. So at 15 degrees C, what you get is 0.06492 plus 0.07586. Probably the values that you will get what 8 7 berapa tak? 7 0.14. Betul tak? I don't know. Is it correct?
Yes, Doctor.
Okay. So this is actually for 15, and the rest you can do the same. Let me check. Yes. So this is basically the how you get the E naught, okay, for cathode at 15, 25, and 35 degrees C. Okay, so this is actually been justified. I didn't show the calculation here. I just show the values, but more or less it's like this. Can you understand this one? I think maybe it's not that difficult to understand, because as we know, according to this reaction, okay, Ag to AgBr is known as the oxidation process. Ag2Br2 to Hg is the reduction process. Then this one, the given potential is actually the potential of anode. This one, this is actually your anode. Anode and cathode. Using this formula, okay, we want to find E cathode, because the question is actually asking for E cathode. Okay, so we just, I think, rearrange it, and then you will get this value. So the rest for 25 and 35, you can do the same. Is it clear?
Yes, Doctor.
Okay. So I believe this one is okay. Then the next question, still in question A, they ask what would be the representation. So since we already know that the equation is basically Ag plus Hg2 Br2, you get Agbr plus Hg. Okay, then maybe we need to like balance the equation a bit. Okay, all right. So for the cell reaction, okay, we can actually divide it into half. Okay, so this actually the equation for cathode, and this is actually for anode. Even though this one, I think I write it in a reduced form, okay? Cathode fraction, get Ag2 Br2 plus 1 electron. Okay, you get Hg2. Okay.
Doctor, should be 2 electron, not 1.
Sorry?
Should be 2 electron.
Yeah, just notice that. Okay, thank you. Thank you, Jihad. Okay.
Welcome.
So meaning that you follow it carefully. Okay, so this one is actually the half equation for cathode, and the half equation for anode will be as this: Ag minus, okay, double head arrow. This one should be double head arrow too. Okay, you get AgBr and okay, plus 1 electron. Okay. Right. So this one you can balance it off. Probably if you want to make it like 2, so this one they make it into half, but if you want to make it 2 also no problem, you just multiply this one with 2, so you get 2, 2, 2, and 2. Okay, then this will cancel off. Okay, this one is 2 will be cancelled off 2, then and you will get the overall reaction will be Hg2 Br2 plus 2Ag arrow 2Hg plus 2Ag Br. It's the same. I mean, like if you multiply this with 2, you will get the same representation. So, yeah.
How did you remove Br ion, Br elements?
Again, Mehdi?
You removed 2Br with another 2Br. This ion element.
This one, 2Br?
Yeah, this
and?
is ion. And this element.
Okay. What do you mean?
So how can remove both of them?
Okay, because the product over here, I consider it as AgBr. It's not forming Ag plus. Okay, so if it is Ag plus, then I will not consider Br. But in the cell reaction, it is mentioned that the product is actually AgBr. It is not written as Ag or comma Ag plus. Okay, then with this, I think we have to address the Br. And as I mentioned earlier, in the question, that Br is actually the common ion. It is used as an electrolyte, okay, because the electrolyte used over here is MBr, okay, metal bromide, okay, any metal, okay, and when you have metal bromide electrolyte, okay, so during the oxidation process, Ag plus will combine with Br minus from this electrolyte to form AgBr. So similarly for this one too. So that is why I think we have to consider Br in this case, right? So the equilibrium constant KQ, okay, or K, you can write it as follows, because this is actually the things, okay. So it will be product over reactant. Then what will be your product? The product will be Hg, and then multiply with AgBr, okay, So we put A actually. A because of the activity over the activity of Hg2Br2. Sorry, this one missing 2. Okay, multiply with activity of Ag. Okay, so what did I miss over
Doctor,
here? Anyone knows?
Doctor, all activities square.
Yes,
Yeah.
except one, Jihad.
Except Hg2 Br2.
Yes, correct. I just want to
Yeah.
say this because I think activity, but we have to make sure that the stoichiometry is written. So we can write it as A2, okay, Ag2 also. This one Hg2 Br2. I think stoichiometry is 1, so no need the power of 1. And for Ag, it's power of 2. You can write it as this one, or you can make it as this one. I mean this one, sorry. No problem. Okay? It's just that over here, later on, you know that for solid, we will not consider the value because solid doesn't have any concentrations or any activity value. So we just remove this, and then we also remove this because Hg and Ag, okay, doesn't have any concentration value. So at the end, you will get K.
Doctor, we can say that the number that mean 1.
We can assume like that because solid normally doesn't have a concentration, and we consider it equal to 1. Okay? Yeah?
Okay.
This will be the forms that you get. Okay, right. So this is actually the first representation, and maybe later on you can substitute into a nurse representation because you know in nurse, E cell is equals to E naught cell plus with RT ln K. So over here, I think we just like neglect the E naught cell. Okay, then we just substitute it. Then you will get the cell. I mean representation. E cell is equal to RT over F ln AGBR over A power of half Hg2Br2, or you can write it also as this way. Right, so since AGBR and Hg2 are solids, their activity didn't change with temperature. So E cell is directly proportional to the temperature. So this will be the first assumption. Right, the half cell of Br minus Hg2Br2, okay, so for the another half reaction is this one, okay, then we can also write the K equal to this, and then E cell is also equal to this. So just now I think we write it for the cell reaction, because I think the question is also asking the cell equation and also for your cathode, for your cathode electrode. So for cathode, this is actually the reaction, the half equation. So you can write it in the form of K, and then you can substitute. So even though this one is not dependent to temperature because it is solid, okay, so the activity of Bi minus is dependent to the temperature because its activity coefficient is dependent to temperature. The dependency of potential to that of temperature gives rise to the more complicated problem. So what is the next question? Calculate delta G, okay, at 25 degrees C for reaction 2 Ag plus Hg2Br2 2 AGBR plus 2 Hg. So they want us to calculate the delta G. So what you need to have, I mean, for delta G. So remember, for delta G, this is actually the formula. We can use Faraday's equation. Okay, Faraday's equation relate that delta G is equal to negative RT ln K. Right? So earlier we have derived this. Okay, and then the K value can be assumed as equals to K2. Then, I mean, when you want to calculate the delta G, okay, so delta G value can be calculated as follows. Okay, it is equal to RT ln K, and then when you actually rearrange it, it will become like, okay, this one is basically equals to negative NFE, okay, because N is actually equals to 1. Sorry, in this case, the N will be equal to 2, because if you look over here, okay, we have seen that the electrons that been produced is 1, but we have balanced it into 2. So N is actually equal to 2. This formula actually tells you that delta G is equals to negative RT ln K, and it is also equals to negative NFE. Right? So since the delta G value is equals to negative NFE not cell, then you can substitute. N is actually equals to 2. Then you will get delta G naught equals to negative 2 multiplied with Faraday's constant, that is 6,500, multiplied with cell potential. The cell potential at what? Anyone knows? The cell potential, we take it from where?
From the previous, we can take.
Okay, so since the question is actually asking at 25 degree, because this is actually standard, where standard normally occurs at 25. Even if I didn't write it at 25, if I didn't write this at 25, when you look delta G naught, then you know that this immediately means that it is equal to 25 degrees C. Then what you need to do is you need to read out from here 25 degree. What will be the value of E naught? This one. Okay, so you take this one 0.06804. You substitute to it 0.06804. Then you will get the value. It's equal to 13,132 joule per mole. Is it clear to everyone? I think this one is quite straightforward. Question C, calculate delta H and delta S for the reaction. So for this one, okay, you need to use Van Hoff equation to calculate delta H and also delta G. Right. So how you can go? I mean, you can get it. So I think first you can calculate delta S. Okay. So you know that from this, I mean, representation, delta S is equal to the change of delta G over dt. Okay. Because E is directly proportional with temperature, So you will get delta S is equal to 2 Fe. This one, I think I have substitute N is equal to 2. Okay. So as I said, over here, and delta G, you know that it is equal to negative RT ln K, or it is also equals to negative NFE. So I just substitute this one to here. Okay, so what will happen is basically NFE, negative NFE over change of T or delta T. Okay, so negative to negative, it will be positive. So you will get delta S is equal to NFE over delta T. So N is equal to 2. Then when you substitute over here, you will get delta S is equal to 2 Fe over change of temperature. Right. So since the question is asked, didn't ask at which region, so you can choose. Over here, the change of temperature, I took it from 15 to 25. Okay, so 15 to 25. Okay, so 15 to 25. Okay, this is actually the E0 value. Change of E. Okay, 25 minus 15, you will get 0.06804 minus with 0.06492. Okay, you'll get that value. I think that is equal to, oops, okay, that is equal to 3.12 power of negative 3, which means 0.00312. Okay, and then the difference of temperature is equal to 10, because 25 minus 10 degree is equal to 10. Even if you convert it into Kelvin, also the same thing. When you subtract the two value, 25, 298 minus 288, then you will get 10 Kelvin. Okay. So what happened over here is that later on you will see that delta S is equal to 2 multiplied with Faraday constant multiplied with 3.12 power of negative 3 over 10. You will get this answer. Is it clear? Is it okay to everyone? Yeah.
Delta E, you take the difference between 25 degrees Celsius and delta E for 10 degrees Celsius?
Yes.
Or
yes.
15?
Yeah.
Okay. Thanks.
Yeah. Actually, Mahdi, if you want to take it from 35 to 25, also you can. Okay? Because normally the E cell.
That's zero. Zero.
No, I mean 35 to 25. Like for example, you take 0.07116 minus with 0.06804.
That's 25. That's 25 to 35.
Yeah, you can also choose 35. I mean, the difference of 35 to 25 also, no problem. I mean, but the potential difference will you take it from here and also here. The value will be slightly almost the same. Difference of temperature is still the same. I mean, because the range is like 10 degree increase. Is it okay?
Doctor, the temperature should be in Kelvin or centigrade?
It doesn't matter because if you change it into Kelvin also, you will, I mean, if you subtract the value, it's still the same. You get a 10 different. But I think since this is thermodynamics, I will recommend you to change it into Kelvin because all values in thermodynamics, the temperature is actually in Kelvin.
Yeah. Okay, Doctor.
Right. So the last one, actually, they ask to calculate delta H. So delta H, you can calculate from Van Hoff equation. Okay. So Van Hoff equation actually give you like delta H is equals to delta G plus with T delta S, right? So this is actually the Van Hoff equation. So since we already have this one, okay, which the value of delta G that we get is at 25 from the previous question, then temperature also will be used at 25 degree, and delta S value is normally the same, okay, then we also have this one. So you just substitute the value, okay, and that is why I put here at 25 degree C, okay, because at 25 degree C we already have delta G value. Then the value that you put over here is 13,132, okay, plus with temperature in Kelvin 298, multiply with delta S 60.22. If you calculate this all together, you will get 4813.56 joule over mole. Okay, this is very straightforward. The last question, actually last question asked about what? The last question, using the Gibbs free energy for the formation. So we have delta G formation, okay, of silver bromide, which the value is equals to negative 95,960 joule over mole. Calculate the free energy formation of Hg2Br2. So how we can do this question? I think maybe if you study in during your what I don't know, A levels or matriculation, or in fact during undergraduate, you might heard about Hess law. Have you ever heard about this one, Hess law?
Yes, Doctor.
Hmm?
Yes.
Yeah, this one is actually in thermochemistry. I think thermochemistry subject, okay, where you can actually calculate the formation of free energy, okay. So for example, like in this case, okay, if you remember the equation for the formation of the product, H2 Br2 will get 2 AgBr plus 2 Hg. Okay, so over here you will see that, okay, the product, okay, this is actually the product and this is actually the reactant. So for the formation, normally we will look on the reactant. What will be the reactant that we use? Okay, then over here, you will see that, okay, for this one, I will consider, okay, AgBr, okay, and also Hg2Br2. So even if you look on the equation, okay, for the formation of Hg2Br2, okay, you will need, okay, like 2 Ag2Br. So that is why over here, you'll see that I multiply it with 2. The reason why is because this one. If you look on the equation, it equals to 2 moles, and this one doesn't have any, I think only 1 mole, so that is why here is just like 1 unity. Okay, then delta G is equals to 2 delta G naught formation of AgBr minus with delta G naught F for Hg2Br2. Okay, so since this value is known, we already have this value, and this value is also given in the question. So you just substitute the value. Okay, then I guess over here you will see that, oh, why this one is become negative? Anyone knows why this one is become negative?
Doctor, here give the delta G naught for AgBr minus 95960.
Sorry again?
In the question, in the example, that give the delta G naught of AgBr 95960
Okay.
minus.
Yes. That is why I'm asking you, where does this come from? I mean, the negative value. So
because that's product.
Yeah, if you look in the question, it is, I mean,
minus.
Here. Yeah, it's minus. Okay, so just to tell you earlier that the minus value is actually coming from the delta G formation. So I mean, you can write it even here. I mean, like 2 multiplied with negative 95,690. Okay, so this one is actually going here, and this one going here. So this value, I mean, the delta G value is actually negative 13132. So when it goes over here, it becomes positive 13132. Then overall you will get negative 178788. Okay. All right. Is it okay? Is it clear to everyone?
Yeah, it's
Okay.
Okay. Formal potential, I guess this one is more or less related with non-standard cell potential, E cell, because we know that in the standard condition, this will be the working condition. But for a non-standard condition, okay, we cannot use E naught, okay, but instead we use it, I mean, E cell, or sometimes they write it E naught prime, okay. So E naught prime is also equals to E cell, okay. So I think I didn't really prefer this, because sometimes some students might confuse because they say they see not. Maybe they say, oh, it is a standard. No, because you see there's a prime over here. Okay, so this actually means that it is a non-standard. But normally they use this to relate it with a formal potential. As I said, formal potential is actually defined as a non-standard condition potential. Then we always call it as E cell. I mean, in those, or in the previous slides before. So you know that you can get E cell, okay, from NERS representation. E cell is equals to E naught cell as with 2.303 R T over F. Gamma oxidant or activity, gamma reduction. Oops. Okay. So reference electrode is normally used as a reference to check what will be the potential values. Okay. So that will be the function of reference electrode, because as I said earlier in the previous lecture, reference electrode is used to measure what?
Potential.
Ya. Siapa tu? Liana ke? Okey. So, baru dengar suara Liana. Kau tak senyap je. Okay. Alright. So, it is constant potential with time, and normally if we return to the original potential, we will trace it as small currents. Right. So, even for reference electrode, we have seen it before. The difference, I think, reference electrode that we might have, saturated calomel electrodes, standard hydrogen electrodes, what else? Silver chloride electrodes. Okay, so all these are actually almost the same thing. It's just that the dimension is different and the potential values is slightly different as well. All right. So the electrode potential measurement normally measures in the two interface. So what will be the interface? So remember that when you do any electrochemical process, okay, your working electrodes, okay, will be oxidized and then forming electrons or whatsoever. Okay, so this one will produce electron. Okay, and then when it produces electron, at the same time, potential value will be recorded or released. So then, in your electrolyte, you also have a reference electrode. So as I said, this reference electrode will capture, okay, the potential value that is produced, and then this will give the information to the voltmeter to later on give what will be the cell potential values. As I said, the electrode potential occurs in the two interface. So what will be the interface? This is actually the interface. It's between metals or working electrode to reference electrode. Okay, so in the environment you have electrolyte. Okay, so that is why over here, when you look at this profile, the phase angle, okay, you will have some distance. Okay, so this distance is actually related with the distance, how far you put your working electrode to the reference electrode. To have a very good potential values in any electrochemical measurement, it is best to place working electrode as near to reference electrode. Okay, so if we put it almost near to the reference electrode, then this actually will result a smaller distance, and the transfer, the charge transfer or the mass transfer in the electrode can occur fast as well. Okay, right. Okay, so probably just a few last part before we call for the day, because I actually feeling a bit tired. But I mean, this morning lecture, probably we will continue the junction potential. I mean, more details on junction potential in the next class, I think next week. But of course, probably I can tell you what does it mean by junction potential. Okay, a slight introduction on junction potential. So, junction potential is basically a potential value produced in a junction in a capillary. Okay, so you might seen some experiments that use a bridge like this, or maybe like a capillary like this. Okay, then there's a porous septum. Okay, so one electrode is placed over here in one compartment, another electrode is placed in another compartment. Okay, electrolyte is being put. Right, so the potential over here and the potential over here is not the same. Probably if it is the same, then the balance or the net of the reaction will be different. So when you look at this, when this experience oxidation, okay, ions will be produced, then it need to travel here through this capillary. Okay, so if you put one reference electrode over here, okay, one reference electrode, the potential in this junction or in this capillary will be different as well. So this potential values in the capillary, we call it as junction potential. Okay, because over here you will have a difference in terms of concentration. Probably over here, if I put like concentration of metals, so you have like more concentration of metals as compared to another compartment, because this actually have more metals as compared to metal ions. So because of the difference of concentrations, then in one compartment to another compartment, then that is why you'll see that the junction potential over here, or the potential value in the capillary, will be different as well. Okay, so the two solutions of the same electrolyte at different concentration. Okay, so that is what Fi is when I mentioned over here that you have one compartment that has slightly higher concentration and another compartment have a lower concentration. So this will create like a gradient or movement. Okay, all right. So the third solution of the same concentration with different electrolyte having the common ion. Like for example, maybe over here you have like what? KCl. Oops. KCl, and over here you have NaCl compartment. So this like a septum or a porous or a membrane. So the common ion over here is Cl. Okay, then this also can give you junction potential effect. Then another condition that will establish junction potential is two solutions that not satisfying number 1 and number 2 condition. So this will be the consideration how junction potential can establish. First, if you have the same electrolyte at different concentration, another one is same concentration, having a common ion, and another one is the two solution that not satisfy number 1 and also number 2. Right. So probably, I guess, a few last slides before we end. During your undergraduates, probably you have heard about transference number. Okay, transference number is basically a fraction of current carried by ions. Okay, so you will see like T plus, T minus, all these are actually related with transference number. Number of ions that can be carried, okay, or transferred. T plus means that positive ion, T minus means that negatively charged ions. You can also have a conductance formula, okay, from junction potential, and also you can get conductivity, okay, from junction potential as well. And for junction potential, okay, the calculation will be as follows. This is actually the formula to calculate junction potential. You have to remember this one. Ej is equals to 1 minus 2t plus multiplied with RT over F ln A plus minus 2 over A plus minus 1. A plus minus 2, A2 is actually a compartment that has a higher concentration. And A1 is actually a compartment that has lower concentration. Okay? All right. So at the end, if you see another relation with E cell, so E cell is actually related with reduction potential minus with oxidation potential plus with junction potential. If this is in the case of when you have that setup, when you have this kind of setup, you have like a capillary that separates Okay, the two compartments. If it is in the standard condition, then you will get E naught. Okay, then this will be the overall cell potential formula. Okay, so I guess maybe the concept of transference number, hit-off methods, like this one, hit-off, and you also have moving ionic boundary, moving ion boundary condition. We will continue next week, Tuesday. So before that, is there any questions so far that you want to ask?
Can you
Anything?
Doctor,
Yeah, Jihad, please.
in the course we have a practical.
Yes, of course, we have a practical.
You the doctor of practical, yes?
Sorry again?
We have labs, some labs.
Yes, of course, we have lab.
Yeah, okay. Yeah, you think about that and you give us a plane.
As what?
You give us a plane for labs.
A plane? What do you mean plane?
Plane, how we do it?
Okay, so for practical, I guess I will schedule like sometimes, but normally you will not going to do the practical now. Normally, if you look on the introduction part, which I have explained earlier, that you will do the practical towards the end of my part, which means maybe in week 6 or week 7 before your
Inshallah.
test. Okay.
Inshallah.
So we just finish all with the theory, and then after that, maybe we have like to spend 1 week for practicals before test. So as I said, normally the practical part for me and Dr. Faiz, we only have like 1 practicals day for my part, and Dr. Faiz 1 part. But I think for my part, we will concentrate more on the electrochemical measurement for corrosion, not for the physical electrochemistry, because this is actually quite fundamental. Some practicals for junction potential, for example, have been taught during undergraduates, but I'm not sure whether you have learned it or not. But if you think that you also wanted to do a junction potential experiment, then maybe we can think of what that. But I think so far the requirement for lab report for my part only 1. Dr. Faiz also 1. So I think maybe we don't have to do like too many labs for I think this course. But for my part, as I said, 1 session you will study all methods. Like later on, you will study about electrochemical impedance, polarization methods, electrochemical noise. So we will do all experiments in 1 day. So yeah, we can finish that. Any other question?
Victor, can you go to 12, slide 12?
Sorry again?
Can you go to slide number 12?
Okay, this one?
Yeah, what's the connection of connection electrodes?
Conduction electrode?
Yes, you put the third electrode here in the middle of the electrode.
I'm very sorry, Mahdi. Your voice is kind of like stuck. I cannot catch really what you are saying. Can you repeat back?
I said, what's the connection of this the connection electrode that means you put at the middle between the cathode and
When we are going to use it?
yeah.
Okay. Maybe because of we have not gone through the hit-off method and also moving ionic boundary methods. Actually, for the hit-off method, if you see over here, you will see that we have, I mean, like the hit-off have performed 1 experiment where he put 1 compartment with a higher concentration of electrolyte, the same, like for example, NaCl, he put like 1 molar. Another one, he put 0.1. molar. So different concentration, and then just to make the circuit complete, he just like make a junction over here. So when these things happen, actually we just want to study the behavior. A higher concentration of ions will tend to go to the lower concentration. So there's a movement, actually, the movement of ions from one compartment to another compartment. So that is why when I say that if you put one electrode over here, you will see, or you will notice that the potential values is not the same as one side and also another side. So it's actually depends on the transference number condition. So in application, okay, I'm not sure whether some of you took separation methods. Anyone took separation methods? But
Yeah,
you will notice that one of the methods in separation is actually you use electrophoresis, capillary electrophoresis,
Yes.
like a gel electrophoresis. So capillary electrophoresis, the concept is you have a gel, okay, and then you have a terminal. You have electrode positive and electrode negative. Then the separation actually happens when you have a movement of ions. Okay, so the movement of ion actually will separate the compounds or whatsoever. Okay, in capillary electrophoresis. So capillary electrophoresis is one of the best application for transference or junction potential. Okay, all right.
yeah, so that means to control the movement of ion charge.
Yeah.
Okay, so much.
Okay.
Okay, I got it.
All right. So any other question? Any further question? Shamira?
No, Doctor. So far, so good.
Shamira hari ni senyap je malam ni. Mungkin agaknya penat kot. Puvina, is it okay for you?
Yes, doctor. Okay.
Okay. Nazira?
Yes, Doctor. Okay.
Okay. Mariam? How about Mariam?
Okay, Doctor.
Okay. And Hamda, I didn't hear Hamda today.
Yes, Doctor.
Yeah, okay. All right. So Madi have 3 accounts registered to join the session today. So I hope that you have submitted your quiz yesterday. Okay, because I think I have extended to 10 p.m. but I haven't checked because this morning I was busy. But probably later on I will check. Do you have any problems so far for the quiz? I believe for quiz 1 is kind of straightforward. Any problem for quiz 1? You guys can do it, Mandy?
There was a problem.
Huh? No problem.
Yeah, no problem.
Okay. All right. So I'm expecting Mahdi to get 20, yeah? 20 over 20. Okay.
Thank you so much.
Okay. All right. So if there's no question, I believe probably today we just end till here. We will continue the next part on transference number next Tuesday. I hope you guys have a good weekend. Okay. And I think later on, I will start to post assignment 1. Maybe by tomorrow, I will start to post your first assignment. It is all in chapter 1. Okay. For chapter 1. So you can start to do it. Normally, I will give like around 1 week time. Maybe if I post it tomorrow, I will put the deadline till Friday next week. Okay, so you have enough time to finish off the assignments and everything. And if you have any question later on, you are pleased to ask me later. Okay. All right. So once again, thank you very much for your kind attention. So with that, thank you very much. Assalamualaikum, and have a very good night to everyone. Goodbye.
Thank you, Doctor.
Thank you, Doctor.
Yeah.
Yeah, thank you, Doctor. All the
Welcome.
best for the workshop. Okay.
Okay. Thank you.